Hi, today in this video I want to talk a little bit about quantum resistance, cryptography in particular, something that called hash-based signature. It's not about building quantum computers and build a chandelier like this. I think this is a picture from IBM. At the moment, there are all these big corporations spend a lot of money building computers, quantum computers like this. But when I look at this, this kind of reminded me of this guy, um, with the early days of computer and all the wiring that I see, and the same typical problems that the quantum computers have today. But there's a little bit of difference here, and uh, that this guy just built both the algorithms and the hardware to break Enigma. But things are a little bit different now. And before I go on, I want to make sure that I stick to my plan and schedule. That this talk would be non-engineers, non-mathematicians. I try to explain the concept as easy as possible. If you just know bits and bytes, that's the only thing you need to know to understand this talk. And I'm trying to basically show you some facts related to these algorithms. So in case you are in charge of buying devices or in dealing with government and those type of things, you have some preliminary knowledge. In particular, if you yourself are building products that are going to last for a while, say a car or some piece of hardware that you want to have for a long time, I think this is the time to think about quantum resistance cryptography algorithm, which is, encryption and signing messages or signing your firmware and that sort of thing. So with that, I'll just start, my discussion about this. And like I said, right now, obviously, the technology advancing a lot faster than it did in 20th century. And also, like I mentioned, the difference is this guy named Shor in 1990s, he came up with an algorithm that's named after him, Shor algorithm. And he basically, this algorithm, uh, if you have a strong enough computer, it can break modern cryptography, the cryptography that everyone has been using for the last 20, 30 years, securing the web and many other things, encryption that you rely on and things like that. I tried to show this. I think it was DALI, Bing AI, and I asked Bing AI, give me a picture where I break a large number into tweaks, and unfortunately it couldn't do any better than this. But anyway, um, just having a little bit fun with generative AI. The cryptography that we have today, we have the RSA, elliptic curve, and Diffie-Hellman. These either rely on breaking a very large number into two primes or solving a problem that's called discrete log problems. And both of these problems are believed to be able to be basically trivial for quantum computers. So the idea of cryptography, when you protect data with encryption or something, is come up with a problem that is very difficult for people to solve. And if the problem suddenly becomes easy, then your algorithm is not good. So why the sense of urgency is because quantum computers are coming along, and the governments are started mandating the use of this algorithm. So various in the last couple of years, governments in Europe and US and elsewhere are mandating this algorithms. And as you can see, the NSA in US came with this mandate called CNSA 2.0, and they're basically showing, this is their timeline. They're showing, as you can see, with the sort of the dotted sort of line is where you need to start thinking about the adoption, and the solid is when you actually need to put it in place. So you can see they have timeline for web browsers, networking equipment, operating systems. And in particular, the one that comes early is software and firmware signing. So if you're building server or a storage or networking equipment that is going to have software, you want to do software updates, you have to use these things to basically do the signing. And in particular, you can see they actually even mandated some algorithms here. And for software signing, initially they want these two algorithms, one of the two, you don't have to do both. One is called a Lighten-Micali signature, and people call this LMS, and the other one an extended Merkle signature, XMSS. You don't need to be able to spell these acronyms. As long as you know LMS and XMSS is good enough. And as far as the other algorithms, AES is something that has been around for quite some time, and this seems to be resistance, and also SHA is a secure hash algorithm. Well, we'll talk about hash algorithm in a bit. These two seem to be okay, but for signing, they want you to move to things like LMS and XMSS. So I'll try to explain these a little bit. So in general, we call these algorithms that can resist quantum computers, quantum resistant algorithms, and sometimes they call it post-quantum cryptography algorithm, PQC. There are two types, and one is called hash-based signature, and the other one is called module lattice. I'm not going to cover the second one in this video, probably in the next one, but I'm going to talk about hash-based signature, hopefully trying to do it in a way that anyone can understand this. So what is a hash-based signature algorithm? Let's just go through what a hash algorithm is. So by the way, these are the three algorithms that are coming along in the selection by the standard bodies. So you see the first two that I mentioned. So what's a hash algorithm? Suppose I always like to talk about potatoes when I see hash algorithm, because hash brown is really one of my favorite things, and potato is. So let's say you have these potatoes and you start cutting them, and you get this. And the idea of hash algorithm is one way. So if you had a piece of data that, like say these potatoes, and you did a hash algorithm, it's very hard from the hash of the message to go back to the original. So in this case, you look at these cut potatoes, it's very hard to put them together and make it the original potato. Obviously, somebody can argue and say, no, I can do this. And yeah, I'm sure some people can do that. So that's why, the finer you do this hashing, the harder it is to go back to the original potato. So whenever you hear a hash function, think about this. The more hashing, the more number of bits you produce from your hash algorithm, that means the better the algorithm is in terms of keeping its one-way property, which means if you have a hash, you don't want to go back. Shouldn't be able to go back to the original message. And in fact, hash algorithms are very good at this. And basically, the harder it is, they call it there's more entropy in the hash. And there are some old algorithms like this that act like this bigger potato chunks, and they're no longer good algorithms like SHA-1 and MD5, and they're better algorithms called SHA-2, SHA-3. So this is just good for you to know. You don't need to know the details of these algorithms. So, I provide some examples here about what these algorithms is. So just remember, if you see SHA-384, that means the output of the SHA is 384 bits. It doesn't mean it's SHA-3. That's a common mistake that you can sometimes see. And the hash algorithm, as you can see, is one property is very important, and that's why Bitcoin mining that relies on hash algorithms, basically the idea is you have to keep trying and trying and trying what's your own ledger and come up with a hash algorithm that have some properties. And that's why you see people set up mining rigs, because there's so much computation involved. So now let's go a little bit further, and basically, let's say you have the hash and now you put some secret sauce on it. Again, that picture is done by Dali. I just told her, give me a bottle that says secret sauce on it, and because I didn't want to have any copyrighted material in here. And so sometimes it works, sometimes it doesn't. In this case, it did a good job, actually. So you can say the secret sauce is my private key. Because I'm signing a message, I don't want, because I'm signing a message sending to someone, I don't want somebody to take the envelope inside, if it was a letter, and change whatever I wrote in the letter and sign it themselves. So it's supposed to be a secret that I only have, that nobody else has. So that's the idea of having a private key. And the use case is basically prove authenticity. If somebody sees the message, it knows that I signed it. Now, on the other hand, this type of signature mechanism relies on a public key that you give to the other side, and then they see the public key and the signature. They do the hash on the message. Then they can say, yeah, you're the one who signed the message. So the idea of public-private key is you can send them their public key so they can check your signature. It's kind of like, the DMV uses your signature on your driver's license, and basically people look at the DMVs and they know that DMV did the thing. Although you can see your signature and they can obviously forge it. So basically the idea is, with the hash and the public key, you can look and say, yes, the message is original. Okay, so now what happens with this quantum resistant algorithms? Now, instead of just taking one hash and one signature, they chop this hash. After you hash the message, you chop it in many different chunks, like that. Obviously, it's the same picture, but imagine these were different chunks of that same original hashed message. Now, for each one of these chunks, you use a different key. And in this case, in terms of these quantum resistant algorithm, it's not like the traditional algorithm. You have to spend a lot of times figure out what this private key is and what the public key is. You just create random numbers and you pretend like that random number is your private key. But you use one public key for each one of these chunks. And basically now you do more hashing on each one of these private keys, and then more hashing to get the public key. So just a lot of hashing. And they call this one-time signature. Is a guy from a long time ago, Winternitz, that came with this idea. So why do they call it one-time signature? Now just a little bit math okay. So I said all of this, I'll move on. This is just the picture that I picked from the standard, because just to explain how this works. So you see the digest was the hash of the whole message. You cut it into chunks, and you can see the chunks, one being 6, the other one is 3, the other one is F, which is a hexadecimal number 1, and so on. So the second line is the private key for each one of those digests. Then, like I said, when you do the signature, you take that private key and you hash it. How do you hash it? If this digest was now 6, you see the digest that was 6, you say, okay, I hash this guy 6 times. If it's 3, I hash this 3 times. And then, because this is a 4-digit number, I said this is the only thing you need to know to understand this video. If it's a 4-digit number, it's basically has a value of 0 to 15, 16 values. So you take and hash this 15 times and you get public key. So as you can see, and then what you do is you have all these chunks, you have these private keys, you created the signature for each one of these chunks. you line them all at next to each other, and when you line all of these next to each other, then you have a signature. So the signature is the total of all this. Now, why this is a one-time signature, I put all this, my Dali pictures here. And by the way, the longer each one of these chunks are, that means the bigger these digits are, here you have to do more hashing. But because each chunk is bigger, you have fewer and fewer chunks, and that means your signature is smaller. But if say you had this signature here, but if the attacker knows the message, it can know the digest, it can calculate the signature. It also knows, let's say I change this 6 to 7 and this 3 to 4 and this F goes to 0, 1 to 2. Basically, all I have to do is take each one of these guys and hash it one more time. So I created my own fake message and my own fake signature. That's why, because the signature and the keys are so simple, you have the benefit of not worrying about a lot of fancy footwork to create the keys, but because of this property, you can only use each one of these keys once. That's why they call it one-time signature, OTS. Things to remember about OTS. First of all, because you use the private key only once, it's called stateful. Stateful means you have to remember things as you go along. So what do you need? You have to remember the keys, which means you can't use a key that you used previously, which means you have to store all the previous keys, which means you need a lot of storage. And then the other thing is, there's a problem with having public keys to be only once, and I go through why that is. It's okay to have private keys being used only once, but public key is not a good idea. And also, as I mentioned, public key and signatures are too long. And then there's a lot of hashing, as you can see. So people look into hardware accelerators. The hardware accelerator means you don't need to run the software for each one of these hashes. You have a hard piece of hardware that does this, which makes it a lot faster. And then remember, the other thing that people think is true is not, is that the SHA-3, which is a new hash algorithm, is not required for these things. Okay, so why can't we deal with one-time public keys and a long public key? As you can see, the private key can get very long, but that's not a problem. If you want to sign your firmware, the firmware, it comes from manufacturers and lands on the device. Let's say you have a car like Tesla, they send the firmware over the air, and that firmware is signed. The signing happens in the factory or where the software is created. So if it's long, it's okay because it's some big computer or some hardware security module, they call it HSM. But it's not okay to have a long public key. Why? Because these devices inside the car or inside server or inside computer or your phone, they don't have a lot of storage, at least for this purpose. So that's why you need to shorten the public key, and then, as I mentioned later, you need to also find a way that public key can be used more than once. So how do we do this? This is something that's called Merkle tree, and I'm not going to go through the whole thing, but the idea of Merkle tree, Merkle is also a guy, I think he did this in 1980s or 70s. So it's basically saying you have a bunch of stuff on each node. Let's say each one of these things is one of your one-time public keys. What you do is you take two, you hash it, you get this guy. You take these two, you hash it, you get this guy. You take these two, you get hash it, this guy. And remember, every time you take two and hash, the length of these things become the same as this length. So as you can think about it, initially you had these 4 lengths, now you have 1 length. You had 8 lengths, you had 1 length. So you had 16 in this case. At the top, you only have 1 length. So if your hash is 256 bytes, These things could be a lot longer, but this thing at the top is 256. This is how they reduce the public key size, and you can shove it inside a small device so that somebody can use and verify that the firmware was authentic. Okay, so I'm using some snapshots from people's paper, and I mentioned the name of people on top of this picture. So these guys basically showing the idea of, okay, these are all those chains that I showed, all these. So if you can think about it, all of this is the chunks of one message, and then together this is the tree to end up to the public key of that message. So you can see one message here, one message here, one message here, one message here, and so on. Now the idea they're talking about multi-signature scheme. Why? Because this public key could be only used for this message. This one only for this message. But let's say now we build a tree, the same thing, the same look at the original tree. And if you, again, keep doing that hashing, you end up with this blue dot, that's the public key. This public key can be used for all of these messages. Why is this good? The reason is, let's say you put that public key in your device memory in your car and you send the car. If you had to use a new public key for every message when you're signing, then obviously that's no good, because over the life of the device or the car or whatever it is, you probably need to send a lot of firmware updates. So the height of this tree, basically a little bit of math here. The height of this tree, let's say that if the height of this tree was 4, means 4 layers up, you could sign 16 messages with this. So that's why people like to increase the height of this tree so that they can sign a lot more messages. But they can do that, but the price that they end up paying is, you know, I'm not going to go through the detail, but the length of the signatures become a lot longer. Now jumping into a little bit of data, and that basically thanks to a company called Keyfactor. There was a very nice post-quantum cryptography conference at the end of 2023 in Amsterdam. So I was watching the videos on internet, you can watch it. And this is data from Keyfactor. And so there's a very good, I'm not going to go through explaining everything, but this is the traditional signature mechanism. And basically, they use a measure which is the level of bits, the difficulty for security, the difficulty of breaking that algorithm. Let's say this is at 128 bits, this is at 192 bits, and this is at 256. The bigger the number, the harder it is to break that algorithm. So these are, you can see the traditional signature algorithms. This is another algorithm that came later on. And here, this is the algorithm that we were talking about, the LMS. And these are some algorithms that I'm not going to talk about these videos, but these are also part of the NSA guideline that not immediately, but just in a few years. This is comparing the signature sizes, and as you can see, you know, the traditional signing algorithm. These are the ones that you see in use today, whether on the web or on software or everything. You can see the signature size is very small, and as algorithms, the signature size is getting bigger and bigger. And the one thing that I probably want to mention before closing this video is these are the two algorithms that I was talking about. This LMS and this. These are, as I mentioned, stateful, which means you have to remember the keys that you used previously, store them somewhere. This is another algorithm that is coming along and is getting a lot of success. This is a stateless algorithm, which means you don't need to remember the keys. And all you need to know for here is that, unfortunately, you don't need to store the old keys. but you pay with a much larger signature size, which basically you send a message and you send your signature along with the message, and people look at the message, they have to verify that the signature is correct, which means the bigger the signature size, the bigger the size of the message, and you need more bandwidth, and you need more storage, and all that stuff. There's another performance comparison that I wanted to show. This might be a little bit more complicated to explain, but if somebody's interested, this is again from this paper. The credit to this paper. It's a very good paper if you want to get into the details of all this. And I definitely learned quite a bit from this paper. And they're trying to kind of do a Shakespearean thing here, to be or not to be stateful. They're showing the performance for these different algorithms. These two are the traditional algorithms. This is the new ones, and this is the stateless one. And what they're doing is, when you want to compare performance, you don't always talk about how many seconds or how many nanoseconds or milliseconds, because it depends on the computer that you're using. The faster the computer it is, the faster the calculation. So they talk about clock cycle in your computer. So the faster, the more clock cycles you need for an algorithm, that means the longer time it takes to run the algorithm. And they compare this if it's done in software versus if it's done in hardware. So this one is the hash algorithm done in software, and this one the hash algorithm done on hardware. And they compare how much calculation do you need to do for verifying a signature, which is usually done in a small device that is receiving the firmware, compared to how much calculation you do the hash. So this is sort of their benchmark. And as you can see, there's new signatures. The one that are stateful actually perform better than the traditional signature algorithm. So it looks like the performance is good. And the reason for that is, and even, you see it's even better in the case of hardware. So basically, this is just a performance comparison that I wanted to show, and basically close this talk. So if you enjoyed this talk, let me know in the comment section, and I can maybe go into more detailed and technical detail or math details, and I can do another video basically going into the second type of post-quantum algorithms, which is modular lattice algorithms. Okay.